Hello once again, Foundation students. Today we're going to talk about ordered pairs and Cartesian products, and we'll also talk about indexed families of sets. The first topic here of ordered pairs, no doubt you have some intuitive familiarity with ordered pairs because you've worked with them in numerous previous classes like algebra and calculus classes. And when we talk about ordered pairs, we're talking about the sort of thing that you've seen before, like where you plot ordered pairs in the plane, 2, 4, and 4, 2, for example. What we want to do is define ordered pairs on the basis of sets, okay? We want to put everything in terms of sets because we're building up a theory and we want it to be consistent, and having everything based on sets is really good. But we want ordered pairs that we define in terms of sets to behave just like ordered pairs behaved in previous classes. So one thing that's important about ordered pairs is order. We want 2, 4 and 4, 2, the ordered pairs, to not be equal. That's important. Our most immediate objective is we want to define ordered pairs in terms of sets. The most obvious thing's not going to work, though. You might think in order to define the ordered pair 2, 4, you might want to take 2, 4 to be equal to just the set containing 2 and 4. But that's not going to work because the set containing 2 and 4 is the same as the set containing 4 and 2. And if your definition of ordered pair was going to work like that, then this would have to be the same as the ordered pair 4, 2. So moral of the story is this is not going to work. So here is what's actually going to work. Definition 2.25 here is how we're going to define ordered pairs. So an ordered pair, A, B, using the same notation as before, we define it to be this set. So A, B is going to be a set containing 2 sets, the singleton A and then the set containing A and B. So an ordered pair is going to be a set of sets. Of course, we call the element A the first component and B is called the second component. There are some fancier terms for those like ordinate and I can't remember. But according to this definition now, let's see. What would the ordered pair 1, 5 be? According to our definition up here, we just put 1 in place of A and 5 in place of B. We get the ordered pair is defined as, okay, to be the set containing the singleton 1 along with the set containing 1 and 5. And if you reverse the order and look at 5, 1, you get the set containing 5 and then the set containing 1 and 5. Now what if you have an ordered pair where both the first component and the second component are same? In that case, it shouldn't matter if you switch the order, right? And indeed, that's what we see happens. The ordered pair 5, 5 would consist of the singleton 5 along with the set containing 5 and 5. But the set containing 5 and 5 there, I'm just listing the same element twice, so that's really just the same as the set containing just one copy of that 5. And now we got the same situation. We've got a set containing 2 of the same thing, so we can just get rid of the redundancy and say this is just the set containing the singleton 5. So when the first component and the second component are the same, it's really true that you can see it doesn't matter if you try to switch the order of those 5s, you get the same result. So hopefully, while this may seem a little bit of a strange way to keep track of order, one thing it certainly does is it puts the definition of ordered pair in terms of sets, which we have all kinds of rules and methods for, which is really important, right? We know how to prove things about sets now. How to prove set equality and set containment. We know how to, we have a long list of properties about sets which we can bring to bear on general sets. So all those properties that we had on sets we can bring to bear on ordered pairs now. So this is a good thing. It seems a little weird at first, but it does what it's supposed to do. It keeps track of order. So now let's look at fact 2.27 here. It tells us, how do we tell when 2 ordered pairs are equal? And thankfully, it works out just like you hope it would. So 2 ordered pairs are equal if and only if their first components are the same and their second components are the same. So that is A comma B equals C comma D if and only if A equals C and B equals D. This may seem like, well, duh, that should be, I mean, like, obviously that's the case, but this is something we have to prove because when we say two ordered pairs are equal, we're really saying two sets are equal. And when we say two sets are equal, we have this stuff about containment, right? One set is contained in the other. Let's prove this. Now notice that the statement that we want to prove here is an if and only if statement. And as such, one way to prove it is to prove both the forward implication and the reverse implication, the converse. So we'll do it that way. So let's prove the forward implication. This is actually the hard direction. The other direction is actually pretty straightforward. Okay, so if we're proving the forward implication, we'll start by assuming that the ordered pair A comma B is equal to the ordered pair C comma D. Then by the definition of ordered pair, we have these two sets are equal. The set contained in the singleton and the set A comma B equals the set containing the singleton C and the set containing C and D, like so. And the way we're going to approach doing this proof is basically we want to consider if this set right here has actually one element or two elements. Just like whenever we were doing the ordered pairs 1, 5 and 5, 1 and 5, 5, these ordered pairs up here, when you write their set definition, actually have two elements, the singleton 1 and the singleton, or the set containing 1 and 5. But when the coordinates were the same, you ended up with just a singleton set here. So we kind of want to look at the two cases that the ordered pair that we're looking at here, A comma B, either has really two things in it, or there's the possibility that those two things are actually the same and it collapses down. And that's really just a matter of whether A and B are equal or not. So the cases that we're going to do are whether or not A and B are equal. All right, so we have these two cases. And so let's do the case where A is equal to B. Well, in this case, well, if A is equal to B, remember that we already know that this set containing the singleton C and the set containing C and D is equal to the set containing the singleton A and the set containing A and B. But in the case that A is equal to B, this set collapses down to just A, the set containing the singleton A. So when you look at what's going on here, you compare this set to the set on the far right, we've got a set with two elements equals a set with one element. So that means that the set on the far left can only have one element. So really, these two sets have to be the same. So that set is a one element set, which means that the set containing C and D just equals the set containing C, from which we surmise that C must be equal to D. So this means that that set that was on the left up here a second ago, this set, since C is equal to D, it just collapses down to just the single element set. So that set actually just equals the set containing the singleton C. And so now when we keep track of what's equal, remember, let me highlight some things here. This set equals this set, which is up here, which equals this set. So that means that this set and this set circled are actually equal. And if those two single element sets are equal, that means that their elements are equal. And then again, that would imply that the elements inside those two single element sets are equal. So we get C is equal to A. So now at this point, if we keep track of everything that's equal, let me put a highlighter pin on some of these things. So we started off by assuming A was equal to B here, and then we found out C is equal to D, and then we found out C is equal to A. So when you stitch all that together, we see that A equals B equals C equals D. So what did we want to prove here? We want to prove that A equals C and B equals D, and that's certainly true. So A equals C and B equals D. So we started with our hypothesis up here of A equals B and C equals D, and in this subcase, we arrived at the desired conclusion. And then we need to do the other case where A is not equal to B. That case is a little bit more complicated. I'll do it on the next page here. So in this case, our set with the singleton A and A comma B, that's really just our ordered pair A comma B, right? Is a 2-element set. If that set is equal to C comma D, also we've assumed that the ordered pair A comma B, ordered pair A comma B is equal to the ordered pair C comma D, so we know that our ordered pair C comma D, which takes this form as a set, is also a 2-element set. Okay? Now remember, these two sets here are equal. So since they're equal sets, we know that the elements of one of the sets are elements of the other sets. So in particular, if I focused on, let's say, let me focus on this element, the singleton A. I know it's in this other set down here, so that element has to either be equal to this element or this element. So there's two possibilities here. So since these two sets are equal, then either singleton A equals the singleton C, or the singleton A equals the singleton C comma D. Now, we can say that C does not equal D, for otherwise, the ordered pair C comma D is a 1-element set, which we know is not so. Remember, up here we said that this set is a 2-element set. So we can't have C comma D be a 1-element set, because that's what C comma D is, this set up here. So I can't have both of those things happening. So C is not equal to D. Thus, we know that this is not the case. This was a possibility that the singleton A equaled the set containing C and D, but since C and D are not equal, then I can't have a 1-element set equals a 2-element set. So we know that the singleton A equals the singleton C, which was the other possibility that we had up here among those two possibilities, but this is the only one that makes sense. So if the singleton A equals the singleton C, then we can say A is equal to C. And that's half of what we were hoping to prove. Now, knowing that singleton A equals the singleton C, and knowing from what we know at the very beginning is that the ordered pairs were equal, which I'm writing in set form here. So we have two 2-element sets that are equal, and we've identified that these elements are equal. So that forces the other two elements to be equal, right? So we know that A comma B equals C comma D. And then the same logic applies now. We know that A equals C, so that forces B to be equal to D. We couldn't have B is equal to C, because that would make A and B equal to each other, which would make this a 1-element set over here, which we know it's not, because we know C and D are not equal to one another. So, and with A equal to C, we know now that B equals D. Whew, that was a lot of work, but we arrived at it finally. We got A is equal to C and B is equal to D as desired. So this proves, that was a bit of a long proof, but this proves that if the ordered pairs are equal, then the corresponding components are equal. A is equal to C and B is equal to D. But that's just half of the proof. That's the forward implication. We also have to prove that if the components are equal, A equals C and B equals D, then the ordered pairs are equal. But that is pretty easy. So let's knock that out real fast and we'll be done with this thing. So doing the reverse implication, we would suppose A is equal to C and B is equal to D. Then it's just a simple matter to say, well, A comma B, write it out as a set. And since we know A is equal to C, we can replace any instance of A with C. And since we know B is equal to D, we can replace any instance of B with D. So this just becomes like so. And then, of course, that's the definition of C comma D there. And we're done. So that's the end of the proof. The cool thing about this proof is that it depended entirely upon knowledge of sets. So we're able to reduce some sort of thing that we already knew about sort of on an intuitive level, ordered pairs, and give it this rigorous foundation on sets, which is really kind of cool. All right, that was a lot of fun. So now let's move to Cartesian products of sets. So for this definition, A and B are sets, and we define the product. Sometimes we call it the cross product or the Cartesian product. So A cross B is the set of all ordered pairs A comma B, where the first component A comes out of the set big A and the second component comes out of the set big B. So it's a pretty straightforward definition. Let's try it out with a very specific toy example here. So if I have A is equal to the set containing little a, little b, and little c, and big B is the set containing 1 and 2, the cross product of those two sets, okay, we form all of the possible ordered pairs where the first component comes out of A and the second component comes out of B. So I could pair A with 1, and I could also pair A with 2, like so. Then I could pair little b with 1 and little b with 2, and then I could likewise pair little c with 1 and 2. And those are all of the ordered pairs you can form where the first component comes from A and the second component comes from B. And so this is the cross product of A and B. A familiar cross product that you've seen before is R cross R. So if we have A and B are both just copies of the real numbers, then A cross B is R cross R. And whenever you cross the same set with itself, you can use this notation if you want, R squared. Now what is R squared? I certainly can't list all of the elements of it like I did in the previous example because R is an infinite set, but this is a set we all know and love, and we have a visual representation of it. You take one copy of R and another copy of R at a right angle to it. Remember, the real numbers can be represented by a number line. And so all of these points in the plane is R squared. So think of this whole plane here. This is R squared. And representative points in R squared, points like 3, 2, that would be an example of a point in R2. But you could also get some strange points with, irrational. So I could have like this point here will be square root of 2, 2. So you get points like that, and so on and so forth. So all the points in this plane are what constitute R2. And so here's an important but a not terribly surprising fact about cross products. If you have a cross product A comma B, which is equal to a cross product D comma E, then it must be the case that the first two sets are equal and the second sets are equal. So, the corresponding sets in the cross product have to be equal here. This is something we can prove in a fairly straightforward manner. Notice this is again an if and only if proof, which means to prove it, we need to prove the forward conditional and the reverse conditional that we call the converse. So we got to prove forward implication and the converse. So let's do that. Of course, we're assuming, just like in the hypothesis of the problem, that A, B, D, and E are non-empty sets. Non-empty is important. If one of the sets is non-empty, then the cross product will end up being empty, in which case the other two sets could be not equal. So non-empty sets is an important part of this thing here. So maybe I'll just go ahead and add that in. A, B, D, and E, non-empty sets. All right, so for the forward implication, we're going to assume A cross B equals D cross E, and then we'll prove that the corresponding sets, so that would be A equals D and B equals E, we'll prove that by double containment. Okay, so we have two sets that we want to prove are equal. I'm going to do this in one fell swoop. So what I mean by that is, by putting this notation here, I'm going to prove that the left-hand set is contained in the right-hand set for both of those equations. So here we're going to prove at the same time A is a subset of D and B is a subset of E. So to that end, we're going to let little a be an arbitrary element of big A, and little b is going to be an arbitrary element of big B. And what we want to do is we want to show that the element A has to be in the set big D, and the element little b has to be in the set big D. So let's see if we can manage that. Since little a is an element of big A, and little b is an element of big B, we have the ordered pair A comma B is in the cross product A cross B. That's the definition of cross product, right? It's the set of all ordered pairs where the first component comes from A and the second component comes from B, and that's what we have here. But we know that A cross B is equal to, by our hypothesis here, A cross B is equal to D cross E. So these two sets have the same elements, and since we know little a, the ordered pair, little a, little b, is in big A cross big B, we know that little a comma little b is an element of D cross E. Then, by definition of cross product, we know little a is in D and little b is in E, because we have little a comma little b, the ordered pair, is in big D cross big E, so that means the first component's in the first set and the second component's in the second set, like so. So notice that we have now successfully argued that we started with little a in big A, and then little a now lies in big D, and similarly little b was in big B, but now little b is in big E. So we arrived at our desired target, so that proves the containment. The reverse containment is pretty similar, so I'm going to tell you that you do it. It would be a good exercise for you to fill in this proof here, just as exercise in proving things involving ordered pairs and cross products. Okay, and then that would prove the set equality A equals D and B equals E. So then we need to argue the converse is true, that if those sets are equal, then the cross products are equal, but that's pretty obvious. If A is equal to D and B is equal to E, then certainly A cross B, which is the set of all ordered pairs A comma B, where little a is in big A and little b is in big B, is going to be equal to the set of ordered pairs A comma B, where little a is in D and little b is in E. But then that's just the very definition of D cross E. So not much to do there. And that finishes the proof. Okay, so here's another problem just to work through, just as an example, just to get used to proving things involving Cartesian products. So for three arbitrary sets, A, B, and C, we want to prove that A crossed with the union, B union C, would be the same as the set A cross B union with A cross C. Since everything is defined as sets, this equality right here is set equality, right? And so we know how to prove two sets are equal. We have methods for that. And in particular, I suggest that we use the double containment method to prove these two sets are equal. So let's do it. So let's prove the forward containment. So I can prove this by taking an arbitrary element, I don't know, let's call it T, in A cross B union C. Now what does it mean that T is an element of A cross B union C? That means that T is an ordered pair, where the first component's coming from A and the second component comes from B union C. So that means T is an ordered pair, let's say X comma Y, where X is an element of the first set in the cross product, which is A, and Y is an element of the second set in the cross product, which is B union C. Well, since Y is in B union C, then by definition of union, we know that Y is an element of B, or Y is an element of C. So there's two possibilities about what set Y lies in. So we'll consider those two possibilities in turn. If Y is an element of B, we have X as an element of A still. So the ordered pair T, which is X comma Y, would be an element of the set, okay, X is in the set A and Y is in the set B. So we know that our ordered pair is in A cross B, but A cross B is certainly a subset of A cross B unioned with some other set. Doesn't really matter what we would have unioned A cross B with. If I union A cross B with any other set, A cross B is a subset of that. So when you look at what you have here, T is an element of the set on the far right. Because, well, it's an element of A cross B, but then that set's contained in there, so that means T is an element of the far right set. So T is an element of A cross B, union A cross C. And so notice our element chasing here. We started with T in A cross B union C, and then we arrived at T was in the right-hand set, right? So that's that. And then going the other way, it's not that much different. Oh, I forgot. Now we have to do the other case too. On the other hand, if Y would have been in C, well, it's not that much different. We still have X is in A still. So our ordered pair T equals X comma Y is an element of A cross C, because the first component's in A and the second component's in C. But again, this is certainly a subset of A cross C unioned with any other set. So we have our A cross C right there being unioned with some other set. It doesn't really matter what it was unioned with. That certainly contains A cross C. So that tells us that T is an element of A cross B union A cross C again. So we had to consider these two cases because Y was in a union. So those cases were here and here, and then we considered them here and here. But either way, we got the same result. If T was in A cross B union C, like we have at the top here, then we got it here and here that T was in the other side. How would the reverse containment go? We let T be an element of A cross B, union A cross C. Well, to be in the union means you're in one of those two sets. So we know T is an element of A cross B, or T is an element of A cross C. So let's consider those two possibilities. If T is an element of A cross B, we have T is an ordered pair where the first component X is in A and the second component Y is in B. Well, since Y is in B, we have Y as an element of the set B union C because B union C contains B. So that tells me that my point T, which is X comma Y, the first component's in A, this ordered pair is in A cross, and then the second component Y is in B union C, so A cross B union C. And then similarly, if T is in A cross C, I'm going to let you fill in the details, but basically just replace B with C and the above proof will work. So similarly, we obtain if T is in A cross C, then T is in A cross B union C. So in this direction, we started with T in this set and ended up with T in, so we started with T in the right-hand set and we ended up with T in the left-hand set. And that completes the proof, having proven both containments. All right, so those are some good practice problems for dealing with ordered pairs. Now, one thing that's interesting about Cartesian products. So why do we care about Cartesian products? Well, it turns out that everything else that we talk about in this class later, in future chapters, is a Cartesian product of some sort. When we talk about relations, relations are a special kind of Cartesian product, or they're a subset of a Cartesian product. When we talk about functions, that's a subset of a certain Cartesian product. So Cartesian products are, the next. First we had sets, and now we got this special kind of set called a Cartesian product. And then all the things that we're going to talk about after this are based on Cartesian products. We just have this really cool hierarchy of ideas going on here. So being able to work with Cartesian products is really going to be important the rest of the way out. So these problems that we've been doing are pretty good examples. Let's have a little skills check here. I've got these 3 problems. The first 2 are pretty straightforward calculation problems, just to check that you understood definitions. The third problem is a proof that's kind of akin to what we did in this previous problem here. It's just proving a property about how Cartesian product interacts with other set operations, like intersection in this case. So take some time to do these. Press pause. And when you come back, we'll run through these together. Okay, welcome back. So the first problem here asks you to express the following ordered pairs as sets. Okay, so that first one, the ordered pair alpha comma beta, the definition says this should be the set containing the singleton alpha along with the set containing both elements alpha and beta, like that. And in the second one, we've got the ordered pair gamma comma gamma. And as we saw from before, whenever the components are the same, it collapses down to a singleton set, where the singleton in that set is itself a singleton containing that one element, which in this case is, phi, not gamma. I like to work in Greek characters just so you get used to writing them. You don't do a lot of that in calculus, but as you get into more advanced mathematics, you start running into more Greek characters, so you have to get used to writing them. I remember trying to get my hand to make Greek characters at the beginning. It was always tough. Okay, number 2, we've got 2 sets. A is set containing 1 and 2. B is a set that contains sets. So B, the elements of B are sets. In particular, we got the empty set as one of the sets in that set, and the singleton alpha is one of the sets in that set, one of the elements of that set. So we want to find the cross product, the power set of A crossed with B. Well, first thing we should probably do is write down what the elements of that power set are. So first, let's do power set of A. Well, the power set of A, remember that's the set of all subsets of A. So one subset is the empty set. Then we get the singletons. And then we get the whole set itself. So now we're prepared to calculate the cross product, power set of A crossed with B. So basically, all we want to do is make ordered pairs where all of the first components of those ordered pairs come from power set of A, and the second components come from B. So I just start with the first element of the power set of A, and that's going to be my first component of an ordered pair. So I'm going to have an ordered pair where the first component is empty set, and then I just run through the elements of B, like so. So I'm going to have the empty set, comma, the empty set, and then I'll have the empty set, comma, singleton alpha, and then I'll have an ordered pair where the first component is 1, and then I'll pair that with empty set, and I'll also pair 1 singleton with singleton alpha, and then we have the ordered pair where the first component is the singleton 2, then I pair that with phi, and I pair that singleton 2 with the singleton alpha. And then lastly, I'll have the ordered pair where 1 comma 2 is the first component, and then second component of empty set, and lastly the ordered pair where the set containing 1, 2 is the first component, and the set containing alpha is the second component. One thing to notice here is that we just crossed a 4-element set with a 2-element set, and notice that our cross product had 8 elements in it. 1, 2, 3, 4, 5, 6, 7, 8. So that's a property that's in general true for finite sets. If you cross an n element set with an m element set, then you're going to get m times n elements in the cross product. Okay, so prove or disprove. For 4 sets, A, B, C, and D, A cross B intersected with C cross D should be equal to A intersect C cross B intersect D. Well, this one turns out to be true, so I will prove it. If it were false, though, you would have to come up with a counterexample. So you would have to come up with 4 specific sets such that that equation does not hold. But it is, in fact, in general true. It's false, though, if you replace intersection with union, interestingly. Anyway, since again, this is like that one problem we did not too long ago. We're proving set equality here. And the way I can handle set equality is to use double containment argument. And that's what I'm going to do. So let me say T be an element of A cross B intersected with C cross D. Then that means that T is an element of A cross B and T is an element of C cross D. So one thing is clear, T is an ordered pair because T is in a cross product. So thus T is equal to some ordered pair, let's say X comma Y, and X comma Y is in A cross B, and X comma Y is in C comma D. So I know that, if I think this through, the first ordered pair equation that I have here tells me that X is in A, and it also tells me Y is in B. But then the second one says X is in C and Y is in D. So I'm just going to write all that down now. So using the definition of Cartesian product, I know that X is in A, also X is in C, and then I know Y is in B and Y is in D. So X is in A and C, and Y is an element of B and of D. So that tells me that X is in A intersect C because it's in both of those sets, and Y is an element of B intersect D. And then that in turn tells me that the ordered pair, X comma Y, is in A intersect C cross B intersect D. In other words, T is equal to that ordered pair is in that. So if you look at what we got here, we started with T was in A cross B intersect C cross D, and now I've got that same ordered pair is in A intersect C cross B intersect D, so that shows that containment. And for the reverse containment, I'm going to let you work that out. Given that you've seen how I did the forward containment, I bet you can work it the other way around. All right, so now we come to a topic that I've noticed some students struggle with. This may be the first topic that I feel like students really traditionally struggle with in sufficient numbers that I kind of worry about it. Conceptually, index families of sets is not terribly complicated, but I think the notation, it just sort of psychologically puts people off sometimes. But I think if you just take your time with it and get comfortable with the notation, I don't know if you've ever had the experience where you open up a book, some sort of math book, and you see, gobs of symbols, like you see terrible looking, stuff like that, and you're like, oh my God, I have no idea what that even means. I certainly get that feeling too. I mean, sometimes it just takes a bit of time to digest mathematical notation and start to feel comfortable with it. And I think index families is one of those sorts of things. But conceptually, I hope you'll see that it's not a big deal. And once you get used to the notation, it's not that bad. Here's the idea. So if you only have a small number of sets that are sort of under consideration, like say maybe 4 sets, and you want to give those sets names and you want to keep track of them, well, if you're only dealing with 4 sets, it's not that big of a deal, right? Like maybe you have the sets, maybe you just name them A, B, C, and D, right? But now if you have, let's say, 1,000 sets to keep track of, well, the alphabet that we use only has 26 characters in it. And so if you start going A, B, C, D, all the way up to Z, you run out of names, right? And so a standard thing that we do is that we use subscripts on sets. So maybe you pick your favorite character, like maybe A, and you go, well, I'll have one called A1, and then I'll have one called A2, and then I'll have one called A3, and so on and so forth, up to A1000. Or if you name things like computer scientists, you'll call them B0. They always start counting at 0, B1, B2, up to B99. I'm actually kind of with the computer scientists on this. When you're doing computer programming, it's very useful to start your counting at 0 for reasons having to do with modular arithmetic. But in any event, I think you've seen people use this kind of notation before, right? Use subscripts to keep track of things, use some sort of counter to keep track of things. It could be even that you have an infinite number of sets to deal with. And we could have an infinite set of labels, like say the natural numbers could service your set of labels to label your sets with. But anyway, we call these subscripts indices. One individual one of these things is called an index, right? So then if we take all of those indices and we gather them up into a set that we call I, or we can give it whatever name we want, but if we gather up all these indices, like for example, up here in this example, then I could gather all those indices up into a set. 1, 2, all the way up to 1,000, right? If I did that, I would call such a set an index set. So far, so good, right? Nothing too terribly complicated that I'm talking about here. It's a very common sense approach to how do you name a bunch of things. Notationally, it makes good sense, and I think the terminology of indices and index set make a lot of sense. So now, what we want to do is, instead of having to list these sets, kind of like I did using a ... sort of thing, I want to have a more compact notation for talking about this collection of sets. And so what we're going to have as notation is that if I open up a curly bracket here and put a sub I, and then I say that those i's are elements of some index set I, that would be an indexed family of sets. Just to be very specific here, for this collection of sets A1, A2, ... up to A1000, the index set is I equals, the set of integers 1 through 1,000, and we can use our notation like this to mean that collection A1, A2, ... up to A1000. Sometimes we use this notation. I'll continue out here to the right. If the index is running through some integers, you can do this. You can say what the starting point is, which is 1 in this case, and then put at the top here the stopping point, 1,000. So these notations all mean the same thing here. I think this is the point where people start to get a little scared of the notation, but hopefully it makes sense. We've got a whole bunch of sets, right? And I don't want to have to use this big clunky notation like this in the middle. I want to compactify it a little bit. And so I give all those indices get a name, like collectively. I lump all those indices into a set and call that set I. And then I just say, hey, I'm going to let I run through all of those indices to get all those sets inside here. So an indexed family is a set of sets. And then we keep track of those sets with a set of indices. Let's play around with a specific example here. This is a bit of a toy example because my index set that I'm going to use only has 5 elements in it. I really don't need an index set if I'm only dealing with 5 sets. For 5 sets, I can just call them A, B, C, D, and E if I want. But this is just to illustrate the concepts, okay? So that's why I'm calling it a toy example. It's not terribly useful, but it helps us understand. Our index set is 1 through 5 in the integers. And for each one of those indices, I'm going to name I. I'm going to define a set in terms of that index. So my index is I, and notice that that index I is part of the membership conditions. So let's write down for A1, A2, A3, what I have in the list here, what these sets ought to be. So what's A1? So if the index is 1, then A1 is the set of all n in the integers with the property. Okay, so now my I is equal to 1, right? So I put I equals 1 here and here, and so then I end up with -2 times 1, which is just -2, less than or equal to n, less than 1, like so. Now what are those integers? Well, if you think about it, this is just going to be comprised of the elements -2, -1, and 0. I don't get +1 because of the strict inequality on the right inequality there. So that one doesn't allow for equality. How about A2? Well, this would be the set of integers and now I've got my I is equal to 2, and so I'm going to put that in here and here into the membership conditions for A2. And so then that becomes -4 less than or equal to n less than 2. So that would be -4, -3, all the way up to what? Well, 1 would be the greatest element of that set. And once you do a few of these, you start to you can sort of accelerate your pace a little bit. Like the next one's going to be -6 less than or equal to n less than 3. So this is just going to be the integers that start at -6 and run all the way up to +2. And then A4 would go from -8 all the way up to 3. And then A5 would go -10 all the way up to +4. Now how about A6? Well, this was a little bit of a trick question. A6 is not defined. See, my index set only included the elements 1 through 5, so I didn't make any definition for what A sub 6 would be because that index 6 is not among the indices I defined things for. So A6 is undefined. And likewise, A-4 is undefined since 6 is not in the index set. And similarly, -4 is not in the index set. Okay? All right. Let's do one that's a little more subtle. Okay, now this time, I didn't name it capital I, but my index set, the set from which my subscripts I are coming, is the set of all natural numbers. So I have an infinite index set. And for each of those indices that are natural numbers, I've got this definition for the set. So let's just write down what some of those sets are. I can't list all of them, right? Because, well, I don't have an infinite amount of time to do that. But we can talk about a few of them and start to get a sense for the pattern of it. Okay, so the very first index that we could consider would be A1, right? I can't do A0 because 0 is not a natural number. Or I can't do A sub -1 because -1 is not a natural number. So the natural numbers start at 1 and then go to, infinity, going through the integers. So A sub 1, according to the definition of our A sub I over here, I'm just going to put 1 in place of I, right? And so then when I do that, I get the set of all real numbers with the property that, okay, I is equal to 1, so it's going to be 1 less than or equal to x less than or equal to 1. Well, that's a pretty boring interval. Notice that these x's are real numbers, and then those real numbers have an inequality that goes with them. So what we're talking about here are intervals on the real number line. And so in this one's a really short interval. It's just the number 1. If I drew this on a number line, then all we're getting is just this 1 point right here. Okay, and then let's look at A2. A2 is the set of all x's in the reals with the property. Now I'm going to put I equals 2 into the formula up here for what those intervals are. If you put I equals 2, you get 1/2 less than or equal to x less than or equal to 2. And if I would draw that on a number line, I'd be talking about this interval right here from 1/2 to 2. And then let's do maybe 1 or 2 more of these intervals. So A3 is the set of all x's in the reals. This time it'll be 1/3 is less than or equal to x is less than or equal to 3. If I draw that on the number line, then I get an interval that runs from about 1/3 right there to 3, endpoints included. And so you can I think you can kind of start to see what the pattern is. The left-hand endpoints of these intervals here are going to be getting closer and closer to 0 as you go to bigger and bigger indices in this indexed family. It's like if you'd go out to, like maybe just go out to A10, then what you're going to get, I'm going to use that interval notation that we're kind of familiar with from calculus. You get 1/10, the interval from 1/10 to 10. And so when you line that up with these other intervals, we get 10 way out here, right? And then 1/10 is going to be really close to 0 here. And then you're going to get this interval that goes all the way out here to 10. So the right-hand endpoint is sort of getting further and further out on the number line, whereas the left-hand endpoint of the interval is kind of snugging up close to 0. So this should have you in mind of thinking about limits. These take some getting used to, but with some practice, you'll get the hang of it. I'm sure of it. So now, let's talk about unions and intersections of indexed families. So if we have a whole bunch of sets like that we'd keep track of with an indexed family, we may want to know what are the common elements to all of those sets. Well, that would be the intersection of those sets. And we might want to know if we took all of those sets in that index family and sort of threw them all together into one big pile, that would be the union of those index sets. So these are our formal definitions for those ideas. So this notation here, the cap, and then we put the indexing information underneath that, like what set the indices are coming from. And then these are the sets that are being intersected. But all this definition here is saying is that these are the set of elements that are common to all of those sets in the indexed family A sub alpha. So notice the condition here is X is in A sub alpha for each of those sets. So these are the common elements, all the A sub alphas. And then the next one's the union. And of course, this is just what I was saying before. To be a member of the union, you just have to be in any one of those sets. So this has the effect of just taking all of those sets and just throwing them together into one big pile. So notice that you've got a forever here and you got a there exists there. This one's the union. But conceptually, it's the same as if you just intersect two sets or union two sets. When you intersect two sets, it's just what those two sets have in common. And to be in the intersection of two sets, the element has to be in all of those two sets. And to be in the union of two sets, the element just has to be in at least one of them. So there has to exist one of the two sets that the element is in. And if you extended this to three elements, the intersection of three sets, an element would be in the intersection of three sets if it's in all three. And an element is in the union of three sets if it's in at least one of those three sets. So this set or this set or this set. So this coincides with what we did with, our former definition of just intersection and union of two sets. So let's take a look at a specific example here. I've got an index set which consists of only 10 elements, 1 through 10. And then I've got a definition for my family of sets, A1 through A10. And I want to find the union and intersection of those. So the union is just going to be where I lump all those sets together into one big set. And the intersection is just going to be what those sets have in common. Okay, so before I can answer the question, what I need to do is I need to write down what those sets are and get an understanding of those sets. So let's do that over here. So A sub, the first index is 1. Okay, so that's the set of integers, n and z, where the absolute value of n is less than or equal to 1. So that would be -1, 0, and 1. A sub 2 is the set of all integers having the property that the absolute value of the integer is less than or equal to 2. And so that would be -2, -1, 0, 1, 2. And I think I see how this works now. So A sub 3 is just going to be -3, -2, ... all the way up to, and then +2, +3. And A sub 4 would be -4, -3, all the way up to +3, +4. And then the very last one, A10, it's going to span from -10 to +10, right? So now, let's answer the question about what the union and the intersection are. Let's do the intersection first. What is the intersection of those A sub i's? Where, by the way, another way we could write this intersection is do I equals 1 to 10, because our index set is a set of integers that runs from 1 to 10. So the intersection from I equals 1 to 10 just means what do all these sets over here on the left-hand side have in common? What's the common stuff? Well, if you think about it, you can see that -1, 0, and 1, that's common to this one, and it's going to be in the middle of all of these sets, right? But if you take anything outside of those three elements, it's not common to all of them. For example, -2, well, -2 is in all of the subsequent sets, but it's not in the previous one. So -2 would not be in the intersection because it's not in A1. Similarly, -3 would not be in the previous two sets, so -3 is not in the intersection. So the intersection consists only of those elements -1, 0, and 1. On the other hand, the union, where you take all those sets and you throw them all, put all the elements into one big pile, notice that these sets are contained in each other as you go up. Like A1 is contained in A2, and A2 is contained in A3, and A3 is contained in A4, and so on and so forth. So when you get the union of them, it's just going to be the same as the biggest set, because the biggest set already contains all the elements in the smaller sets. So the union is just going to be the same as A10. Let's try another. In this example, our index set is the natural numbers. So now we've got an infinite number of sets to think about. Whenever this happens, you usually have to sort of start thinking in terms of limits a little bit. You have to. It's not like we're literally going to be doing limits like we do in calculus, but you have to be thinking along those same lines. So our index set is the natural numbers, and for each natural number, we have an interval of real numbers that spans between 0 and 1 over I. So when I is equal to 1, this is going to be an interval between 0 and 1. When I is equal to 2, this is going to be an interval from 0 to 1/2, and so on. So let's write down some of those sets and maybe even draw some pictures just to conceptualize things. So we got A1. So A1, I'm just going to draw a picture of it. And then I'll do likewise for A2, A3, A4. So A1 is going to be the interval from 0 to 1. 1's not included, so it's going to be like, we use these open and closed circles to indicate what the interval is, like this. And then A2 is going to be, so here's 1/2, open circle. And then A3 looks something like this, 0 to 1/3. And A4, something like this. And we got to keep doing this dot, 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 right, forever, ad infinitum. But we can see, I think just doing A1 through A4, we can certainly see what's going on. These intervals are getting smaller and smaller. Now, if you go out and do like A100 or something like that, there would still be an interval there. It would just be a really tiny interval. It'd be like, here's 0, and then you'd hardly be able to see the difference between them. So it's even a little bit of an exaggerated difference, but it'd be a tiny interval that the left endpoint is included in, but the right-hand endpoint is not. Okay, so now ask yourself, what do these intervals have in common? All of them, all infinitely many of them. And that's how you get the intersection. So the intersection of those A sub i's, I and the natural numbers. Well, when you think about it, there's only one number that's common to all these intervals, and it's that left endpoint of 0. There cannot be a number larger than 0 that's common to all of them, because what'll happen is eventually, like here's 0, no matter how tiny of a number you pick, no matter how close it would be to 0, eventually our interval would look like this, and it would miss that x. And if x is larger than 0, there's eventually going to be an interval that moves to the left of that x, and so that x won't be in all of those intervals. It won't be in the intersection. So the only thing that's in all of them is just that one element, 0. And for the union, if you go and look at all these intervals, notice that they're all they get smaller and smaller, so that like there's a there's a containment to them, right? There's like a, I'm kind of indicating it in pink there. A1 is the largest interval. It contains A2, which in turn contains A3, which in turn contains A4, and so on and so forth. So if you union them, you throw them all into one big pile, you're just going to get A1, which is the biggest interval of them all. So if I use the interval notation, it would be the half open interval, half closed interval from 0 to 1, where 0 is included, but 1 is not included. All right. Here we come to a theorem. It's De Morgan's laws for index sets. So De Morgan's law always has to do with how you negate something. And when you're doing sets, negating a set is what we think of as complement, right? A complement of a set is everything that's not in the set. So if you take the complement of the intersection of a bunch of sets, what you get is the union of all their individual complements. And similarly, if you take a union of a bunch of sets and then take the complement after you've unioned them, it's the same thing as intersecting all of their complements. One thing that will help us do this proof is to understand a little bit of logic. So sort of going back to the definition of intersection, if we say x is in the intersection of a bunch of sets A alpha, that means that x is in all of those sets, right? So in other words, for every alpha, x is in A alpha. That's just how you would say x is in all the A alphas. So if you negate that, if we take this logic over here on the right-hand side and negate it, we'll get what it means for x to not be in the intersection of all those A alphas. So remember, when you negate a universally quantified statement, it becomes an existential, and then you negate the condition that it has. So to say x is not in A alpha means exactly there exists an alpha in I such that x is not in A alpha. So X is not in at least one of those A alphas is what it means for X to not be in the intersection. And we can play a similar game with logic. If X is in the union of a bunch of A alphas, that means that X is in at least one of those A alphas. So negating that, we find out what it means to say X is not in the union of a bunch of A alphas. It means exactly that for every alpha in I, X is not in A alpha. So armed with this logic right here, we can prove this De Morgan's law in pretty short order. I'll do part 1. I'll leave part 2 for you to do because it's kind of similar and it would be a good exercise for you. So for proof of part 1, so what we're proving is the property about the complement of the intersection here. Again, I want to emphasize this equal sign here is set equality. And we have methods for proving things about set equality. In particular, our go-to method is double containment. So I'm going to do a double containment proof to prove part 1 up there. So check it out. To prove the forward containment, I'll let X be an element of the complement of the complement of the intersection of all those A alphas. Okay, that in turn means X, what it means to be in the complement of a set is that X is not in that set. So we can say X is not in the intersection of those A alphas. But that's the logic that we already worked out here a second ago. If X is not in the intersection of a bunch of A alphas, that means there exists some alpha such that X is not in that A sub alpha. So according to what we worked out earlier, this means there exists an alpha in I such that X is not in A alpha. And then for the next step, the only thing I'm going to do is point out that whenever you say X is not in A alpha, we can state that in a more positive way by saying X is in the complement of alpha. But now I will point you to this logic up here in the upper right-hand corner. Whenever we see that there exists an alpha such that X is in, an A alpha, that means that X is in the union. So X is in the union of these things, though, with the bars on top. So this tells me that X is in the union of all those A alpha bars. And now check it out. We started off with X here, and then we wound up with X here. So we started with X in the left-hand set, and we argued X was in the right-hand set. So that proves that containment. The reverse containment goes very much the same way. If I would take X in the union of the A alpha bars, that means that there exists an alpha in the I's such that X is in that particular A alpha bar. But then, all I'm doing is reversing the logic from the previous proof. This means that X is not in A alpha. And then we use this logic from right here again to see that, that just means that X is not in the intersection of all those A alphas because it's not in one of them. It's not common to all of them. But then that's what it means to be in the complement of a set when you're not in it. So X is in the complement of all those A alphas intersection. So again, we started with the point in the left, and this time we started with the point in the right-hand set, and we argued it's in the left-hand set. And that completes the proof of part 1. So part 2 would go very similarly. All right. So if you get past the scariness of the notation, the ideas are pretty straightforward. But I realize right now this could indeed look like gobbledygook if you're not feeling comfortable. So this is a good place where the good thing about watching a video is that you can simply press pause and take some time to absorb it for a second before you move on. If you're doing this in a live lecture, you don't have time to sort of absorb and you don't have that chance to put a pause button. Of course, in class, one can always raise their hand and ask a question and buy themselves some time or ask a clarifying question. But right now, your best bet is if something's not making sense, figure out where that point is and then press pause and then don't move on until you figure that out. And if you can't figure it out, that's a good time to come see me and get some questions asked. get some questions answered, maybe. All right, so now's a good time to do a skills check. I just have a couple of questions here I want to ask you involving index families of sets. In the first problem, it's a small indexed family with only 10 elements. And I just want you to write down what some of those sets are, A1, A3, and A7. And then I'd like you to find the union and intersection of those 10 sets. And then here's a little bit more complicated one where the index family is, or the indexing set is infinite, the natural numbers, and then those sets are intervals, kind of like the one I did a minute ago. I highly recommend you draw pictures of these intervals so that you can visualize what they look like and what their sort of endpoints are tending toward in the limit. But again, the same question as before, get the intersection and union of those sets. So take some time, work on these, and when you think you've got them figured out, we'll come back together and work through them together. All right, welcome back. Okay, so for part A on number 1, A1, the elements that we're talking about are coming from the natural numbers, which are positive integers, right? So there's a little bit of a trick here that putting this -2 on here. But A1 would be, you'd be getting -2 less than t less than 1. There are no natural numbers that can satisfy that inequality because the very smallest natural number is 1, but this interval only includes things less than 1. So A1's the empty set. A3 are those natural numbers satisfying the inequality -2 less than t less than 3. And the only natural numbers that satisfy that inequality are 1 and 2. So this would be 1 and 2. And then A7, sort of following the same logic, would be 1, 2, all the way up to 6. Part B, what would be the union and intersection? Well, the union of those AIs, this is again one of those examples where as the index grows, the set that you get next is bigger than the one that comes before or contains the one that came before. So the union of all these sets is just going to be the biggest one of them, which would be A10. So this will be A10, which are the integers 1, 2, all the way up to including 9, but not 10. And then the intersection is what those elements of all those, what elements are in common to all those sets. But notice that A1 doesn't have any elements whatsoever in it. So that means that all of those sets can't have any common elements. So the intersection of all those AIs is going to be the empty set. There are no common elements because one of those sets doesn't have any elements. If you were starting at 2, you would get an intersection of just 1, the element 1. All right, let's take a look at number 2. So for number 2, we have an infinite indexing set. The indexing set is the whole set of natural numbers. And then for each of those elements in our indexing set, the natural numbers, we define these sets A sub n. And when I originally put this problem in front of you, I put an I there instead of an n. Hopefully you picked up on that was a little mistake of mine. Probably apologies for that. But in any event, each of these A sub n's is a set of real numbers. And then this compound inequality over here is defining an interval of real numbers. And then notice that n appears here and here, so each value in our indexing set is giving us a different interval. So let's think, maybe, sometimes it's helpful to think about interval notation. So as an interval, this is the closed interval, and on the left-hand side, it's -1 minus 2 over n, and on the right-hand side, it's 2 minus 1 over n, and both endpoints are included. What I usually do on these type of problems is I plug in I plug in some values and get some specific instances of those intervals so that I can sort of start to see a progression of what those intervals are doing. So I might go over here and look at A1, A2, A3, A4, and see if I start to see sort of a pattern. And each of these is going to be an interval. So let me put a number line down for each of these, and we'll just plot things on a number line to see what these intervals are doing. And one thing I want to mention, Since our indexing set is the natural numbers and our variable is n here, it's clear that n can go to infinity, right? N can get as large as you want it to be. So it probably makes sense in this interval to think about what happens when n gets large. When n gets large, the left-hand endpoint here is getting close to -1 because the 2 over n would get close to 0, right? N gets very large. And likewise, 2 minus 1 over n would get close to 2. So these two numbers, -1 and 2, are very special places that I think we need to pay attention to. So maybe on my number lines, let's put down -1 and 2. Let's make special note of those places on the number line. Another thing, too, is when we put tick marks on our number lines, we should make them line up. That'll make it visually easier to inspect what the pattern is that's going on as n gets large. Go on my number line here, and let's see, maybe I'll put -3 sort of on the far end. Now, A1, when you plug 1 in there, what do you get? Well, you get -1 minus 2, so you get -3. And on the right-hand endpoint, you'd get 2 minus 1, 1. So -3 to 1 is your interval, like so, for A1. And then for A2, that means you put n equals 2 in here. With n equal to 2, you get -1 minus 1, so -2 on the left, and 2 minus a half, so 3 halves on the right. So let's draw that on our number line. Okay, so I get that interval. A3, similar sort of process. I'm going to put n equals 3 in here and get my interval A3. I do -1 minus 2/3. That would be -5/3. And if I plug in 3 on the right-hand side, I'd get 2 minus 1/3, so that would be +5/3. So -5/3 would be hereabouts, and then +5/3 would be here somewhere. So we end up with this interval. And then let's do one more. I think I kind of see what's going on with this thing at this point, though. So put in n equals 4. To get a sub 4, you'd get -1 minus a half, so -3 halves on the left-hand endpoint. And 2 minus 1/4 would be 7/4 on the right, so -3 halves and +7/4, so somewhere about in there. So you can kind of see what's going on with these intervals. This left-hand endpoint is getting closer and closer to -1 here, and this right-hand endpoint is getting closer and closer to 2. So now we can start thinking about what the intersection and the union are. Let's start with the intersection. So the intersection would be the points that all these green points have in common over here. All these green intervals. What do all of them have in common? Well, one thing to think about here is that because these left-hand endpoints are converging in on -1, no point to the left of -1 is going to be included in the intersection, because eventually these intervals, move past any points that are to the left of -1. So all these points over here are not going to be in the intersection. And similarly, if we look around what's going on at +1, there is nothing in the intersection to the right of +1 because that first interval doesn't have any points to the right of +1. So the intersection is going to have to live in this region right here in the middle between -1 and +1. And so then you just have to ask yourself, are the endpoints included? Well, is the endpoint -1 included in all those intervals? So if we focus on these -1s here, is that point included in every one of those intervals? Yes, it is. And likewise, is +1 included in all those intervals? Well, it's included in the first one, and then those intervals just grow to the right of that. So yeah, +1 is in all those intervals too. So your intersection is going to be -1 to +1, endpoints included. Now how about that union? Okay, well, this just means to take all those green intervals and just sort of lump them in together, right? Well, that first interval starts at -3, so I know that, and that's the interval that goes the furthest to the left. So it looks like this union is going to start at -3, And then it looks like you're getting all the points in between all the way up to at least this point here, -7/4. But those right-hand endpoints keep pushing closer and closer to 2, right? But notice that those right-hand endpoints never make it to 2. 2 is a place they never quite reach. They get close, but never quite there. So what I'm seeing when I look at the union, I'm seeing everything between -3 and all the way up to, but not quite getting close to 2. So I would express that as the interval -3 and then up to 2, but not included with 2. So use the parenthesis there to indicate 2 is not included. Well, you'll have plenty of problems like this to practice in homework, so don't despair if this seems a little hard. With a little practice, you'll get good at it. All right, so today in the second lecture on videos, we talked about Cartesian products and we talked about indexed families of sets, both of which are really important topics as we move forward. The topic of Cartesian products especially, everything that we're going to talk about from this point forward is going to be based on Cartesian products. I love how this class has this sort of like build-up of everything's based on the previous thing, this sort of hierarchical structure. First we talked about sets, and then now we've got this special kind of set called a Cartesian product. And you'll remember when we were doing proofs involving Cartesian products, we were using the methods we learned in how to prove equality of sets and set containment, because Cartesian products were just a special kind of set, right? Well, the next topic that we're going to talk about in the next chapter is relations. And relations are just subsets of Cartesian products. So we have a whole big Cartesian product, and then we restrict it to some special subset, and we call that special subset a relation. And relations are important because relations model things like less than, or equality, or modular congruence. There's all sorts of relations you can think about. One number divides another number is a relation. And these ideas of relating numbers or relating mathematical objects can be captured with ordered pairs. So that's subsets of Cartesian products. And then when we move to the next chapter after that, we're going to talk about functions. And functions are just special kinds of relations, which are special kinds of sets. So it's really cool how all this builds up. I really like it. Okay, so I'm going to stop there, and we'll be talking again soon when we meet again to talk about relations. So until then, goodbye.